ICEbox. So ICEbox is a mnemonic, and it's a way of being able to calculate what the equilibrium concentrations are given a Keq value and the initial reactant concentrations. So the ICE is a mnemonic that stands for stands for initial concentrations of everything. C is the change that occurs, and it occurs stoichiometrically. And E are the equilibrium concentrations. So it sometimes helps to just go through it to see what's going on. So the first example, given the following reaction, carbon solid plus oxygen is combusted to create carbon monoxide gas, CO gas. So if 6 moles of oxygen gas are reacted with solid carbon in a 2-liter container, what are the equilibrium concentrations of each species? So first and foremost, as we always have to do, we always have to write the Keq expression first. So I said if the Keq value is 3.6. So Keq is equal to carbon monoxide concentration squared over the oxygen concentration. Notice that there is no carbon in here because carbon is a solid and it doesn't have any concentration units attached to it. I also have to remember that these are concentration units, so because my oxygen gas is given in moles in a 2-liter container, I need to convert that to molarity. So again, I have my Keq expression. It's equal to 3.6, which is given. I take out the solid, and I have to convert anything into concentration units that are not in concentration units already. So the first thing that I do is I write out the equation. So 2C plus O2 yields 2CO. And I go ahead and cross out the carbons because they're not going to be part of my equilibrium concentration expression. So what I need to do is to just take it out so that my future self doesn't make a mistake and start going in circles. Just cross it all out. So my initial oxygen concentration that I calculated earlier, right here, is 3 molar. And there's nothing in the gas that's carbon monoxide. I'm at the start of my reaction. All I have is carbon and oxygen. As it reacts, for every mole of oxygen that gets used in the combustion, 2 moles of carbon monoxide are created. So in the change, I write minus X for O2 because I'm losing oxygen as it gets converted. And I add plus 2X. The 2 corresponds to the coefficient here. And I'm adding it because I'm creating my product. So again, I'm losing my reactant, I'm creating my product. And then at equilibrium, my concentrations are going to be 3 minus X for oxygen and 2X for my carbon monoxide. Again, no carbon because it's a solid. So I keep my Keq expression and then I simply plug these values in. 2X squared over 3 minus X is equal to 3.6. So then I solve for my X value. I have a quadratic. And one of the things that's important to remember that if I have something that's at equilibrium, I have to have both products and reactants present. That's one of the criteria of a system being at equilibrium. So that helps me define what my X values have to be in reality. I have to have an X value that's greater than 0, because I have to have products present. And it has to be less than 3 because I can't subtract more than what I have of my oxygen gas. So my concentration of X has to be somewhere between 0 and 3. So when I solve and I plug this into a quadratic equation formula, because this is an X squared function, I should get 2 roots, mathematically speaking. But these parameters of the X having to be between 0 and 3, help me choose which X value. So because I can't have a negative concentration, and that doesn't fall within my range of 0 to 3, I choose the X value of 1.25. Again, math tells us what the numerical possibilities are, and we have to choose as chemists what the realistic possibilities are. So because there's no such thing as negative concentration, I'm choosing the X value that falls within the acceptable range. So that's my X value, and then I plug it back in here. So CO is going to be 2X, so 2 times that, or at equilibrium it will have a concentration 2.5 molar. and oxygen will be 1 minus that x, 3 minus that x, or 3 minus 1.25, or 1.75 molar. So again, this tells us that if this is my Keq value, and if I start out with 3 moles per liter of oxygen gas, once my reaction reaches equilibrium, I should expect to be able to have 1.75 moles per liter of oxygen gas and 2.5 moles per liter of carbon monoxide gas. Here's a second example. The decomposition of HI. So I'm starting out, and my Keq value, which has to be given, is 2 times 10 to the negative fifth, and I'm starting out with 4 moles per liter of HI gas. So I do this stoichiometrically, right? I start out with no hydrogen and iodine, and all I have is hydrogen iodide gas, and I subtract stoichiometrically. So this side is going to lose, which is why I have a minus sign here, and I'm going to gain products, which is why they have plus signs. I'm going to lose this in a 2 to 1 to 1 ratio. So for every 2 moles of HI gas that I lose, I create 1 mole each of hydrogen and iodide gas. So these coefficients here match the coefficients that are in my balanced equation. My reactants I'm losing, I'm gaining products. And then my equilibrium is simply just adding these 2 rows together. So my equilibrium concentration is 4 minus 2x, and my equilibrium concentrations for both H2 and I2 are x. So I write my Keq expression, H2 times I2 over HI equals 2 times 10 to the negative fifth, and I plug in these values. So x and x equals x squared, and then 4 minus 2x quantity squared is right here. So then I do this all out, right? I first square this, FOIL this all out, and then I bring it to one side. So this is equal to this. I multiply it by x, and then I'm going to be solving for my x value. So first I need to figure out where my bounds are, right? What are the acceptable range? I have to have both products and reactants there. So my x value has to be greater than this because I have to create products. And it has to be less than 2 because I have to have reactants. Right? If x is equal to 2, then I will have no reactants left, and if it's greater than, I don't even know what that looks like. So knowing that, I choose the x value that fits that parameter, and that is 0.01773. That's a very small number, but that makes sense. It makes sense because my Keq value is very small, right? So remember that my Keq value is 2 times 10 to the negative fifth. My Keq value gives me a sense of my ratio of my products over my reactants. And if this is very small, this means that I won't make much product for the amount of reactant that I'm giving, right? Because it's a ratio. My numerator is going to be very small. My numerator are my products. So it makes sense that my x value is very small. And so if I plug this back in, then I find that my x value is going to be, here, 0.01773, and then my concentration from this would be 4 minus 2 times the quantity, 0.01773. So here's the thing. If my Keq value is so small, in comparison especially to my initial concentration of my reactants, then what happens is that this change that I see is negligible, meaning that the difference between my initial concentration and my equilibrium concentration for my reactant is not going to be noticeable, not something that I can measure with the precision of my instrumentation. So what you would see on the graph is that I see an increase in my product concentration, right? Because 0 and something there is a difference. But the difference here between what I've lost is going to be too small to register it. So the example I have is Bill Gates versus me, right? So Bill Gates is a billionaire. I'm not. So if he loses $10 or $100, he's really not going to notice, right? Say that he drops $10 out of his pocket, and at the end of the day, when he's going through his whole entire fortune, he's not going to really register that $10 is missing. However, if I find $10 on the ground as our product right here, and I didn't have any money in my wallet to begin with, wow, that $10 is huge. So when the Keq value is really, really small, which means I'm not going to be losing a lot of reactant to create product. And if it's so small, especially in comparison to the initial concentration of the reactant, then what we can say is that the initial concentration of my reactant is equal to my equilibrium concentration. So you may say, well, so I'm saying 4 minus 2x is pretty much just 4. So you say, well, how can that be? Well, because if you are comparing this, say that I just assume that, and instead of plugging in 4 minus 2x, quantity squared from my HI concentration, I just plug in 4, I end up with an x value of 0.0089, which is pretty close to the 0.01773. So it's within my range of acceptable values. This is called the 5% rule. So the 5% rule is if my initial concentration is at least 10 to the third times greater than my Keq, then I can say that my initial concentration is equal to the equilibrium concentration of my reactant. You always have to check to see if it can be applied because it makes life much, much easier. Why 5%? 5% tends to be a benchmark that we use in statistics to see whether or not the change that we see is within the acceptable limitation of the instruments that are given to us. You'll notice that all of our glassware in the lab has a plus or minus 5% because that's the ishness, the uncertainty that's given in a value. So the 5% rule basically says that if I have such a discrepancy between my initial and my Keq value for my reactant, then the change that I see is going to be too small for any of my instruments to register. It will be as if I'm shaving off my eyebrows. I'm not going to see that much of a difference. So what does that look like in real life? So here's an example. This is the dissociation of silver chloride into silver ion and chloride ions. My Keq value for this is 1.6 times 10 to the negative 10. This is not a very soluble product at all. Very little of it dissociates, most of it stays as my solid. So asking to calculate the silver and chloride concentrations at equilibrium. Well, I write my Keq value, which is silver ion concentration times chloride ion because those are aqueous, but I X out my silver chloride because that's a solid. So all I have are the concentrations of my aqueous ions, and that equals 1.6 times 10 to the negative 10th. That equals x squared, and each value is my silver and my chloride concentration because for every mole of silver chloride that dissociates, I create a mole of silver ions and chloride ions, and that becomes 1.26 times 10 to the negative 5th. That's a really, really small amount. So that's saying no matter how much silver chloride I put in, for every liter of solution that I have, only 0.000126 moles per liter of silver ions and chloride ions will be created. And our final example, I have the dissociation of ammonia gas into hydrogen gas and nitrogen gas. So let's say that I start out with a 6 molar concentration of ammonia gas, and my Keq value is 2 times 10 to the negative 8th. So I do my check. Can I assume my 5% rule? And is my Keq value at least 10 to the third times smaller than my initial concentration? Another way of saying this is, if I multiply my Keq value by 10 to the third, will it still be less than my initial concentration? And the answer is yes, because 10 to the negative 8 times 10 to the negative times 10 to the third is 10 to the negative 5th. That's way smaller than 6. So I can assume the 5% rule, which means that at equilibrium, even though my H2 and N2, I'm adding those, and I'm saying that they exist, 3x plus x here, this is going to be the same, my initial and my equilibrium concentrations. Because the amount that I lose, the minus 2x that I would be losing, is so negligible, I can't tell the difference. So then I plug this in. I write my Keq expression first, so it's H2 cubed times N2 over NH3 squared. Again, the coefficients become the exponents. And so I plug in these values. This becomes 3x cubed, this becomes x, and this becomes 6 squared. Ignore that. It looks like a point, but that's not a point. So that's equal to my given Keq value. So 2 times 10 to the negative 8th is equal to 27x to the 4th. So remember that this cubed applies to both the coefficient and the x. That becomes 27x cubed times x. That's 27 times x to the 4th over 36, which is 6 squared. So I then multiply both sides by 36, and then divide both sides by 27, and then I take the 4th root, and x ends up being 1.27 times 10 to the negative 2nd molar. So that means that's my N2 concentration. That was my x value, right? So my N2 concentration at equilibrium is 1.27 times 10 to the negative 2nd, and my H2 concentration is 3 times that, 3x, or 3.81 times 10 to the negative 2nd, and my NH3 concentration is still 6 molar. In reality, it's 6 minus 0.0254, but the difference between 6 and 6 minus 0.0254, or am I getting 0.0254, that'd be 2x, is so negligible with the instrumentation that I have that I wouldn't be able to notice that.